close your eyes. Not yet, of course. You still need to see these words or hear them wherever you are right now. But soon. Soon your eyes will grow heavy and your breathing will slow, and the room around you will fade into something soft and dark and safe. Tonight, we are going to travel somewhere that no telescope has ever reached. Somewhere no spacecraft could ever fly to, no matter how much fuel it carried, no matter how many centuries it traveled. Tonight, we are going to ask a question that sits right at the very edge of human knowledge. A question that scientists whisper to each other in quiet offices and lecture halls, turning it over and over, the way you might turn over a smooth stone in your palm, feeling its weight, feeling its mystery. The question is simple to say. It is almost childlike in its simplicity, and yet it may be one of the hardest questions ever asked. What existed before the Big Bang? Just let that question settle over you for a moment. Don't try to answer it yet. Just let it rest there, like a single snowflake landing on your open hand, cold and delicate and strange. Before there were stars, before there were galaxies spinning slowly in the dark like pinwheels made of light, before there was a single atom of hydrogen drifting through empty space, before there was space at all, in the way we understand it, before there was time itself, ticking forward second by second, the way it has ticked forward for your entire life, for every life that's ever been lived on this small blue world. What was there? Tonight, we're not going to rush toward an answer. We're going to walk there slowly, the way you might walk down a quiet forest path at dusk, in no hurry at all, letting the shadows lengthen around you, letting your mind loosen and drift. Because the truth is, nobody knows for certain what came before. And there is something deeply comforting in that, if you let it be comforting. Not knowing means there is still room for wonder. Not knowing means the universe still has secrets. And secrets are things you can drift off to sleep thinking about, turning them gently in your mind like pages in a book you never quite finish and never need to. So settle in. Pull the blanket a little higher. Let your shoulders drop away from your ears. Let your jaw unclench. And let's begin, very slowly, to walk backward through time, all the way to the beginning of everything. And then, if we can, just one step further. Right now, wherever you are, there is a kind of quiet settling in. Maybe you can hear a fan humming somewhere. Maybe rain against a window. Maybe nothing at all. Just the soft, nothing sound of a quiet room at night. Hold on to that feeling of quiet for a moment, because it's going to help us later, when we talk about a silence far, far deeper than any silence you have ever known. We live inside something enormous. You already know this in an abstract way. You know that the Earth is a sphere, turning gently in space, held in a long, slow orbit around a star we call the Sun. You know that the Sun is one star among hundreds of billions in a galaxy called the Milky Way. And you may even know that the Milky Way itself is just one galaxy among hundreds of billions of others, scattered across the observable universe like grains of sand on some impossibly vast beach. All of that, all of it, had a beginning. Not a beginning like a birthday party with balloons and candles. A beginning stranger than anything in ordinary experience. A beginning where space itself came into being, where time itself started to flow. Cosmologists, the scientists who study the origin and shape of the universe, call this beginning the Big Bang. It's a name that can be a little misleading, and I want to gently set that misunderstanding aside before we go any further, because it might be sitting somewhere in the back of your mind right now, and I want you to feel light and unburdened as we drift through tonight's story. The Big Bang was not an explosion happening at some location, inside some pre-existing empty space, the way a firework explodes in the night sky above a summer field. There was no field, there was no sky. There was no above or below, no here or there for anything to explode into. Instead, the Big Bang describes the moment space itself began expanding, everywhere, all at once, stretching and unfolding the way a balloon stretches as you blow into it. Except there was no balloon, and there was no air. And there was, as far as we can tell, no outside surface for anyone to stand on and watch. Try to imagine that, gently, without straining. Imagine there is no outside. Imagine there is nowhere to stand and observe the very beginning from a safe distance. The beginning was not something that happened somewhere. The beginning was the origin of somewhere itself. This is the part where most nights, most documentaries, most books, they stop and say, and that is where our story begins. But tonight, we're going to ask one more question. We're going to ask what came before that. And to even approach that question honestly, we first need to understand, slowly and carefully, what scientists actually mean when they talk about the Big Bang, what evidence convinced them it happened, and where exactly the edge of their knowledge lies. Because the before question isn't really a question about ancient history. It's a question about the very nature of time. And to understand that, we have to go gently, one idea at a time. The way you might climb down a set of stairs into a cellar, one step, then another, feeling for the next step with your foot before trusting your weight to it. So let your mind rest here for a moment. No pressure to understand everything all at once. Tonight isn't a lecture, it's a lullaby made of physics. Let the ideas wash over you like slow waves. And if you drift off before we reach the end, that's all right. The universe has been patient for 14 billion years. It can wait for you to finish the story tomorrow night. Let's start with what scientists are quite confident about, because this confidence itself is comforting. It's built on more than a century of careful observation, of scientists pointing enormous telescopes at the sky, night after night, decade after decade, patiently gathering light that has been traveling toward us for millions, even billions of years. In the early 20th century, an astronomer named Edwin Hubble was studying distant galaxies, and he noticed something strange. The light coming from these galaxies was shifted toward the red end of the spectrum. If you've ever heard an ambulance siren change pitch as it drives past you, dropping from a high note to a lower one, you've experienced something called the Doppler effect. Light can do something similar. When an object is moving away from you, its light stretches out, shifting toward red. When it's moving toward you, its light compresses, shifting toward blue. Hubble found that almost every distant galaxy he studied was shifted toward red. And more than that, the farther away a galaxy was, the faster it appeared to be moving away. Now, close your eyes and imagine dots painted on the surface of a balloon. As you slowly inflate that balloon, every dot moves away from every other dot. And the farther apart two dots start out, the faster they seem to separate as the balloon expands, simply because there is more rubber stretching between them. This is, in a very simplified way, what Hubble discovered about the universe. Galaxies aren't flying away from us because we are at the center of some explosion. They are moving apart because the space between them is stretching, everywhere, all the time, gently and continuously, like that balloon's surface. And if space has been stretching for a very long time, if you run that expansion backward, like rewinding a film, you eventually arrive at a moment when everything, all matter, all energy, all space, all time as we understand it, was compressed into an extraordinarily hot, extraordinarily dense state. That moment, or more precisely, the process of expansion beginning from that state, is what we call the Big Bang. Scientists have another beautiful piece of evidence for this story, something called the cosmic microwave background. Imagine, if you will, an ancient light, the oldest light that can possibly reach us, a faint glow left over from a time when the universe was only about 380,000 years old, an infant, cosmically speaking, barely a heartbeat into its long life. Before that time, the universe was so hot and dense that light couldn't travel freely. It kept bouncing off charged particles, trapped, the way fog traps a beam of light in a forest. But as the universe expanded and cooled, atoms formed, and suddenly space became transparent. Light was set free, and that ancient light has been traveling through the expanding universe ever since, stretching as space stretches, cooling as it stretches. Until today, it arrives at our telescopes, not as visible light anymore, but as faint microwaves, a whisper of warmth, just a few degrees above absolute zero, scattered evenly across the entire sky in every direction you could possibly look. When scientists discovered this cosmic microwave background in the 1960s, quite by accident, two researchers named Arno Penzias and Robert Wilson kept picking up a strange, persistent hiss in their radio antenna and initially thought it might be pigeon droppings interfering with their equipment. It became one of the strongest pieces of evidence that the universe really did begin in a hot, dense state and has been expanding and cooling ever since. So let this settle into you now, softly. We have very good evidence that the universe as we know it, its galaxies, its stars, its planets, its light, emerged from an incredibly hot, dense state roughly 13.8 billion years ago and has been expanding ever since. That part of the story is, as much as any story in science can be, settled. But here is where things become gentle and strange and mysterious again, because when physicists try to run the clock backward, all the way back, past 380,000 years, past the first 3 minutes when the first atomic nuclei formed, past the first fraction of a second, they eventually reach a point where their equations simply stop working. They reach what is called a singularity. Have you ever seen one of those old maps, the kind explorers used centuries ago, where the known coastlines are drawn in careful detail, and then, past the edge of what anyone had actually seen, the mapmaker would simply write, "Here be dragons." It wasn't that dragons were actually there. It was an honest admission. We don't know what's out there. We've reached the edge of what we can honestly claim to know. The concept of a singularity, in physics, functions a little like that phrase. When cosmologists run their equations for the expanding universe backward in time, they find that at time zero, the very beginning, the density of the universe and the curvature of space would both become infinite, not extremely large, infinite. And in physics, when your equations spit out infinity as an answer, it's usually a signal that the equations themselves have broken down. It's not that nature is actually infinite in that spot. It's that the mathematical tools you're using have reached the limit of where they can honestly describe reality. Think of it this way, gently. If you're using a paper map to navigate a city, and the map simply ends at a certain street, with blank white paper beyond it, that doesn't mean the city ends there. It means your map ends there. The city keeps going. You just don't have the map for it. The Big Bang singularity is very much like that blank edge on the map. Our best theory of gravity, Einstein's general relativity, describes the universe beautifully across an enormous range of scales, from the orbit of planets to the bending of light around galaxies to the stretching of space itself. But general relativity was never designed to describe what happens when all the matter and energy in the universe is compressed into an infinitely small point. At that scale, another set of rules should start to matter enormously. The rules of quantum mechanics, the strange and beautifully strange physics that governs the behavior of the very, very small. And here is the honest, humble truth that I want to rest gently in your mind tonight, like a small stone placed carefully on a shelf. Physicists do not yet have a complete theory that successfully combines general relativity and quantum mechanics. It's called, informally, the search for a theory of quantum gravity, and it remains one of the greatest unsolved problems in all of science. Without that theory, we cannot honestly say what happened at the very instant of the Big Bang, let alone what happened, if anything, before it. So when someone asks, what existed before the Big Bang? The most honest scientific answer, spoken plainly, is, we don't fully know, not yet. But, and this is where our journey tonight becomes so much more interesting than a simple shrug of the shoulders, we don't fully know is not the same as we have no ideas. Physicists have spent decades developing thoughtful, mathematically serious, deeply creative hypotheses about what might have existed before or instead of that initial singularity. Some of these ideas suggest that the question itself might not even make sense. The way asking, what is north of the North Pole, doesn't quite make sense. Others suggest that our universe might be one bounce in an endless cosmic rhythm, expanding and contracting forever. Others suggest we are just one bubble in an endless, frothing sea of universes, each one with its own Big Bang, its own laws of physics, its own quiet and unknown fate. Tonight, we're going to visit several of these ideas, one at a time, slowly. The way you might visit different rooms in a vast, quiet museum after closing time. When the lights are dim and there's no one else around, just you, wandering peacefully from exhibit to exhibit, in no hurry at all. Take a slow breath in and let it out. Let's go a little deeper. Before we can talk about what came before the Big Bang, we have to sit with a much stranger question. First, what does before even mean at the very edge of time? In ordinary life, before is one of the most natural words we know. Before breakfast, you woke up. Before you fell asleep last night, you probably brushed your teeth. Time flows in one direction for us, moment after moment, and before simply means earlier along that flow. But time itself, according to Einstein's theory of relativity, is not some separate universal river flowing outside the universe, carrying events along on its current. Time is woven together with space itself, into a single fabric physicists call space-time. Time is not a stage on which the universe performs. Time is part of the performance. This matters enormously for our question tonight, because if time itself began at the Big Bang, if the Big Bang wasn't just the beginning of matter and space, but the beginning of time as a dimension, then asking what happened before the Big Bang might be a little like asking what is south of the South Pole. Try picturing the South Pole for a moment, resting there in the endless white quiet of Antarctica. Every direction you could possibly walk from the South Pole is north. There is no further south. South, as a direction, simply runs out at that point. It's not that there's a mysterious hidden region south of the South Pole that we can't see. It's that the concept of south itself stops applying there. The question, what's south of the South Pole, isn't a deep mystery waiting to be solved. It's a question built on a small misunderstanding of how directions work at that particular point on the globe. Some physicists, including the brilliant physicist Stephen Hawking, working together with James Hartnell, propose something remarkably similar about time and the Big Bang. In their idea, known as the no-boundary proposal, time doesn't come to a sharp, jagged edge at the Big Bang. Instead, as you trace time backward, it gradually transforms and behaves more and more like another dimension of space, until, at the very beginning, there is no distinct before at all, just as there is no south of the South Pole. The universe, in this picture, simply is, complete and self-contained, with no boundary, no edge, no starting gun going off within a pre-existing silence. I want you to sit with that image for a while, because it's genuinely one of the most beautiful and calming ideas in all of cosmology, at least for me. And maybe it will feel that way for you too, as your eyelids grow heavy. The universe, in the no-boundary proposal, doesn't need a cause outside of itself, because there's no outside and no before for such a cause to have existed in. It's less like a beginning, and more like the curved surface of a sphere, complete unto itself, with no edge to fall off of, no starting point marked with an asterisk. Every point on a sphere's surface is much like every other point. There's no special beginning location on a globe, and in this proposal there is, in a similar way, no special beginning moment when you look at time from just the right mathematical angle. Does this mean nothing existed before the Big Bang? Not exactly, and this is important, so let it settle gently. It means the question, phrased that way, might be built on a misunderstanding of how time behaves near the very beginning. It's not that scientists are hiding an answer from you, or that the answer is simply nothing. It's that the very structure of the question may quietly dissolve as you approach the beginning. The way a path through a forest might dissolve into open meadow, not because the path was blocked, but because it simply stopped being a path at all and became something else. Rest with that for a moment. There is nothing to solve here tonight, just an idea to hold gently, like a warm stone in your palm as your breathing slows. Now let's talk about another idea, one that doesn't try to erase the before question so much as push it back a little further, into a strange and fascinating chapter that most physicists believe happened in the very first fraction of a second of our universe's existence, a process called cosmic inflation. Imagine, if you can, an impossibly brief moment, far shorter than the blink of an eye, far shorter than anything you could ever perceive, a tiny fraction of a second after whatever we call the beginning. during which the universe expanded at a staggering, almost unimaginable rate. In that unimaginably short interval, space is thought to have stretched by a factor of at least 10 to the 26th power, and possibly far more. If a single grain of sand were inflated by that same factor, it would swell to a size larger than the entire observable universe is today. This idea, called inflation, was proposed in the early 1980s, largely by a physicist named Alan Guth, along with important contributions from other researchers like Andre Linde, Paul Steinhardt, and Andreas Albrecht. It wasn't invented just to sound dramatic. It was proposed because it elegantly solved several very real puzzles about the structure of our universe. Why the cosmic microwave background looks so remarkably uniform in every direction, even in regions that, without inflation, would never have had time to interact with each other and reach the same temperature. Why the geometry of space appears to be so close to perfectly flat, and why we don't observe certain theoretically predicted particles called magnetic monopoles. Inflation, in other words, wasn't dreamed up to answer the "what came before" question. It was proposed to explain patterns we actually observe in the sky today. And it just so happens that inflation opens a fascinating door onto our question tonight. Here's why. If inflation is correct, then the era of extremely rapid expansion may not have had a single sharply defined beginning at all. Some versions of inflationary theory suggest that inflation, once it starts, tends to continue forever in most places, even as it ends locally in small pockets, creating what amounts to an endless, frothing process, sometimes called eternal inflation. Picture, if you will, a vast pot of water at a rolling boil, endless and steaming in the dark. Now and then, a bubble forms somewhere within that boiling water, a little pocket where the water briefly behaves differently before it dissolves back into the larger boil, or grows and separates, floating up as its own little world. In the eternal inflation picture, the vast inflating expanse of space is like that boiling pot, stretching and stretching without end, while every so often, in some tiny region, inflation locally stops, and a bubble universe forms, expanding and cooling and settling into ordinary physics, eventually giving rise to its own Big Bang-like beginning, its own stars, its own galaxies. If this is correct, and I want to be gentle and honest with you here, this is still very much a hypothesis, elegant and mathematically compelling, but not yet confirmed by direct observation. Then our own universe might be just one such bubble, one small pocket of settled space within a vastly larger, endlessly inflating background that has no beginning and no end, that simply always was and always will be, boiling and frothing and producing bubble universe after bubble universe, on and on forever. In this picture, there might genuinely have been a before our Big Bang, an eternal, inflating background, vast beyond imagining, of which our entire observable universe is just one tiny, forming bubble. Let that image drift through your mind for a while. An endless, quiet, boiling sea stretching in every direction forever, without beginning and without end, and somewhere within it, countless bubbles, each one blossoming into its own universe, its own galaxies, its own stars, its own quiet nights, where creatures somewhere might be lying in warm beds, wondering about their own beginnings. Breathe slowly. There is no rush to understand all of this tonight. Just let the image rock gently in your mind, the way a boat rocks softly on calm water. Let's step even further back now, into an idea that sounds almost like poetry, though it comes from some of the most rigorous mathematics in modern physics. The idea that the universe might have emerged from what we casually call nothing, through the strange rules of quantum mechanics. Now, I want to be very careful and gentle with this word, nothing, because in everyday language, nothing simply means the complete absence of anything at all. No space, no time, no energy, no laws, not even emptiness, because emptiness itself is a kind of something. Philosophers sometimes call this true, absolute nothingness, and it's honestly unclear whether physics, as a discipline built on describing things that exist and interact, can meaningfully say anything at all about such an absolute void. But physicists sometimes use the word nothing in a more specific, technical sense, referring to what's called the quantum vacuum. And the quantum vacuum, despite its name, is not truly empty in the way we might imagine. It's a term describing the lowest energy state of a quantum field. And quantum fields, according to quantum mechanics, are never perfectly still. There is a beautiful and strange principle in quantum physics called the Heisenberg uncertainty principle. And one of its many consequences is that even in a vacuum, tiny fluctuations of energy are constantly, spontaneously appearing and disappearing, popping in and out of existence so briefly that they can never be directly permanently observed, appearing for the barest sliver of an instant before vanishing again. Physicists sometimes call these virtual particle pairs, and while it might sound like idle theoretical speculation, this quantum jitter of the vacuum has actually been measured indirectly in real experiments here on Earth, through subtle effects it has on atoms and light. The vacuum, in other words, is not silent. It hums, ever so faintly, with possibility. Some cosmologists, including physicists like Alexander Vilenkin, have proposed that our entire universe might have emerged through a process a little like this, quantum jitter, except on a cosmic scale, a spontaneous quantum fluctuation that instead of quickly disappearing the way ordinary virtual particles do, somehow tunneled into a stable, expanding universe, the way a tiny seed of ice can sometimes form spontaneously in perfectly still, supercooled water and then rapidly grow, transforming the whole body of water around it. In this picture, the universe wouldn't have emerged from absolute philosophical nothingness. It would have emerged from a quantum vacuum, a strange, jittering almost nothing, that still obeyed the laws of quantum physics. Laws that, in this view, might not themselves require space or time to already exist in any conventional sense. This raises, of course, an even deeper and gentler question, one that tonight I want to simply leave floating in the quiet dark of your mind, rather than trying to answer. Where did the laws of quantum physics themselves come from? Were they always there in some sense, independent of space and time, waiting patiently for a universe to obey them? Or does that question too dissolve the way the south of the South Pole question dissolved, built on assumptions that simply don't hold at the very edge of existence? We don't know, and that's all right. Some of the smartest people who have ever lived have devoted entire careers to circling this question, gently, respectfully, without ever fully answering it. You are in good company tonight, drifting through the same mystery that has occupied brilliant minds for generations. Let your breathing slow further now, in and out, in and out. Let your thoughts become soft and slow, like the fluctuations in that quiet quantum vacuum, appearing gently and then fading away again, without effort, without struggle. Let's drift now toward a very different, very old idea, one that has appeared in one form or another across many of humanity's oldest cultures and philosophies, long before modern physics existed. The idea that the universe doesn't have a single beginning and a single end at all, but instead moves through an endless repeating rhythm, expanding and then contracting and then expanding again, over and over, in a cosmic breath without beginning or end. Ancient Hindu cosmology, for instance, described vast cycles of creation and dissolution, measured in spans of time so enormous they make even the age of our universe seem modest by comparison. Many ancient cultures, gazing up at the stars, imagined time itself as a great wheel, turning endlessly, rather than a straight line with a fixed starting point. Modern physics has developed its own, mathematically rigorous versions of this ancient intuition, generally referred to as cyclic models or bouncing cosmologies. In these models, rather than beginning at an infinitely dense singularity, our current expanding universe was preceded by a phase of contraction, a slow collapse of a previous universe, which eventually reached an extremely dense, extremely hot state, and then, instead of collapsing all the way down to a mathematically infinite singular point, it bounced, reversing course and beginning a new phase of expansion, the phase we currently find ourselves living inside. Physicists like Paul Steinhardt and Neil Turok, for example, worked for years developing a model sometimes called the ekpyrotic universe, drawing partly on ideas from string theory, in which our observable universe is imagined as a three-dimensional brain. Think of it, gently, as an enormous, thin sheet floating within a higher dimensional space. And our Big Bang was triggered by the collision of our brain with another such brain, a kind of vast, slow cosmic collision, releasing enormous energy that we experience from the inside as our own Big Bang. In this picture, before our Big Bang, there existed another brain, another slice of a higher dimensional reality, drifting slowly through a vast, higher dimensional space, eventually colliding with our own. And in that collision, our universe as we know it was born. And this process, in some versions of the model, might repeat endlessly, collision after collision, expansion after expansion, contraction after contraction, cycle after cycle, without any true beginning and without any true end. Other bouncing models don't require extra brains or extra dimensions at all, but instead suggest that as the universe contracts and its density climbs higher and higher, quantum gravitational effects from that still unfinished theory of quantum gravity we talked about earlier, become strong enough to halt the collapse before it reaches a true singularity, and to gently reverse it, launching a new phase of cosmic expansion. There's something deeply, quietly comforting about this family of ideas, at least to me, and maybe it will feel that way to you too tonight, as your body sinks a little deeper into your mattress, and your thoughts grow slower and softer. In the cyclic picture, nothing is ever truly, permanently lost. The universe doesn't end in some final, empty silence, nor does it begin from an abrupt, causeless nothing. It simply breathes, in and out, expansion and contraction, endlessly, like the slow rise and fall of your own chest as you breathe right now, in the dark, drifting gently towards sleep. In and out. Expansion and contraction. On and on, perhaps forever. Let's linger a little longer on the idea of a cosmic bounce, because there's a particular, mathematically detailed version of it that I find especially soothing to think about at night, called loop quantum cosmology. This idea grows out of a broader research program called loop quantum gravity, one of several serious scientific attempts to build that still missing theory of quantum gravity we talked about earlier, a way to describe gravity itself using the strange granular rules of quantum mechanics. In loop quantum gravity, space itself is imagined not as a smooth, continuous fabric that can be divided infinitely into smaller and smaller pieces, the way you might imagine cutting a piece of paper in half, and then in half again, and again, forever. Instead, space is imagined to have a kind of graininess to it, a smallest possible unit, far, far smaller than an atom, smaller even than anything we could ever hope to directly observe with current technology, a fundamental quantum of space itself. The way light comes in discrete packets called photons, rather than a perfectly smooth, continuous stream. If space really is grainy at its very smallest scales, then it may be physically impossible for the universe to ever be compressed down into an infinitely small, infinitely dense point, the singularity that ordinary general relativity predicts. Instead, as a contracting universe approaches that extreme density, the underlying graininess of space itself is thought to generate an enormous outward quantum pressure, powerful enough to halt the collapse and reverse it, causing the universe to bounce back outward into a new phase of expansion, well before it could ever reach a true, mathematically infinite singularity. Researchers working on loop quantum cosmology, including physicists like Abe Ashtekar and Martin Bojewald, have developed detailed mathematical models of exactly this kind of bounce, and their calculations suggest that, in this framework, our Big Bang might not have been an absolute beginning of time at all, but rather the bounce itself, the turning point of an enormous contraction phase from a previous universe, a previous era of existence, compressing down, 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 until the deep, quantum structure of space itself gently, powerfully, push back. I want you to imagine this now, softly, as a picture rather than an equation. Imagine an enormous universe, full of galaxies and stars, slowly, slowly contracting over unimaginable spans of time, growing denser and hotter as it shrinks, the way a great tide slowly withdraws from a beach, pulling everything inward, inward, inward. until it reaches a point of maximum density, a single, impossibly compressed moment. And then, instead of vanishing into nothing, instead of collapsing into an infinite point, it bounces, like the tide turning at last, and begins to flow, back outward again, expanding, cooling, spreading galaxies and stars, and light out across a growing darkness once more. Our Big Bang in this picture was not a beginning from nothing. It was a turning point, a bounce. The outward breath following a long, slow inward breath that had been happening for who knows how long, in a universe that, before our Big Bang, might have looked strange and unfamiliar to us, or might have looked remarkably similar to our own, full of its own galaxies, its own stars, its own quiet nights. Let your own breathing follow that same rhythm now, if it helps. Slowly in, reaching a gentle peak, and then slowly, slowly out, like the long exhale of a contracting universe, finally turning outward again into a new, expanding dawn. In and out. Before we continue further into these ideas, I want to pause with you for a little while, here in the quiet middle of our journey, and simply let things settle. You've traveled a long way already tonight, through balloons stretching with painted dots, through ancient light traveling across billions of years, through singularities and blank spots on old maps, through the strange nature of time itself, through a hypothesis where before might not even mean anything, through an unimaginably brief moment of inflation stretching space by more than 1 trillion times, through an endless boiling sea of bubble universes, through the strange jitter of the quantum vacuum, through ancient cyclic cosmologies and modern bouncing universes, and colliding brains drifting through higher dimensions. That's a great deal of vast, strange territory to have walked through. It's all right if your mind feels a little hazy now, a little soft around the edges, the images blending gently into one another, the way dreams sometimes blend together just before you fully wake, or just before you finally fully sleep. There's no test at the end of tonight's story. There's no need to remember every detail, every name, every model. What matters is simply this: that you've spent some time tonight resting your mind on the biggest, gentlest questions there are. Questions that connect you, quietly, to every human being who has ever looked up at the night sky and wondered where all of this came from. You are not required to solve the mystery tonight. Nobody has, not yet. You are only required to rest. So let your body sink a little deeper now, wherever you're lying. Let your hands go soft and heavy at your sides. Let your face relax, your forehead smooth and untroubled, your jaw loose, your eyelids heavy, heavy, heavy. We have a little more of the story left, some more rooms in this quiet, dim museum to wander through together. But there's no rush at all. If you drift off now, that's more than all right. That's exactly what this story is for. And if you're still here, still listening, still gently curious, then let's continue, softly, into the last few rooms. Let's talk now about an idea that stretches the imagination even further outward. An idea sometimes called the multiverse. The hypothesis that our universe might not be the only one, that there might exist other universes entirely, each with its own space, its own time, its own laws of physics, forever separated from our own, forever unreachable, forever unseen. We already touched on one version of this idea earlier, when we talked about eternal inflation and its endlessly forming bubble universes. But the broader idea of a multiverse takes several different forms in physics, each one arising from a different area of research. And I think it's worth wandering gently through a few of them tonight, the way you might wander through a garden with many different, strange and beautiful flowers, none of them quite like the others. One version comes from that eternal inflation model we already explored, an endless, inflating background producing countless bubble universes, each one potentially having different physical constants, different strengths of gravity, different masses for fundamental particles, different numbers of dimensions even. In this picture, there might exist, somewhere unimaginably far beyond our own observable universe, entirely different worlds, operating under entirely different rules, so different that stars might not even be able to form there, or so similar that creatures very much like us might be lying in beds very much like yours, listening to stories very much like this one. A very different version of the multiverse idea comes from an interpretation of quantum mechanics itself, called the many worlds interpretation, first proposed by a physicist named Hugh Everett in the 1950s. Now, this idea isn't really about what came before the Big Bang directly, but it touches our story in an interesting way. So let's rest here a moment. In ordinary quantum mechanics, particles can exist in strange combinations of multiple possible states at once, until they're measured or observed, at which point they seem to choose one definite outcome. The many worlds interpretation suggests, instead, that every possible outcome actually happens, but in separate, branching universes, each one just as real as the others, endlessly splitting off from one another with every quantum event, everywhere, throughout all of time. If this interpretation is correct, and it remains a genuinely open, deeply debated question among physicists without a firm consensus, then reality itself might already be an endlessly branching tree of universes, splitting and splitting again, moment by moment, and the question of what happened before our Big Bang might simply be a small branch on an unimaginably vast, ever-growing tree whose roots and shape we can barely begin to comprehend. There is also the idea, arising from certain interpretations of string theory, of what's sometimes called the string landscape, an enormous number of mathematically possible ways that the extra, curled-up dimensions predicted by string theory could be shaped and folded, each different shape potentially giving rise to a different universe, with different physical laws, different fundamental particles, different values for constants of nature that, in our own universe, seem to be finely and precisely tuned to allow atoms, stars, chemistry, and eventually life itself to exist. Some physicists have wondered whether this fine-tuning might be explained, at least in part, by the multiverse. If there truly exist an enormous, perhaps even infinite number of different universes, each with different physical constants, then it wouldn't be so surprising that at least one of them, ours, happen to have just the right combination of constants to allow galaxies, stars, planets, and eventually, someone lying quietly in the dark tonight, wondering about all of this, to exist. In an infinite garden of universes, the argument goes, at least one flower is bound to bloom in just the right way. I want to be gentle and honest with you about something important here though, before we drift onward. The multiverse, in any of its forms, remains firmly in the realm of hypothesis. It is mathematically serious, deeply explored by brilliant physicists, and it arises naturally from some of our best current theories. But by its very nature, other universes, if they exist, would likely be forever cut off from our own, forever unreachable, forever unobservable, at least with anything resembling our current understanding of physics. This makes the multiverse hypothesis very difficult, and by some scientists' standards, perhaps even impossible, to test directly, which is why some researchers remain quite skeptical of it, even while others find it a natural and elegant consequence of our best theories. Science, at its best, holds space for both the excitement of a beautiful idea and the humility to say, clearly and honestly, we don't yet know if this is true. Tonight, we get to hold both of those feelings gently, side by side, the way you might hold two smooth stones, one in each hand, feeling their different weights, without needing to set either one down. Rest now, for a moment, with the image of countless universes, blooming like countless flowers in an endless, quiet garden, each one unaware of all the others, each one perhaps containing its own version of a quiet night, its own version of someone drifting slowly, slowly towards sleep. I want to pause here and talk with you for a little while, quietly, about something that isn't really physics at all, but that I think matters just as much, especially at night, when the questions we ask ourselves tend to feel a little larger, a little heavier, than they do in the bright, busy light of day. It can feel uncomfortable at first to sit with a question as big as what existed before the Big Bang, and to hear again and again that nobody fully knows the answer. We're used to questions having answers. We look things up, we ask, and someone tells us. But the biggest questions, the ones that sit right at the very edge of what human beings have managed to understand so far, don't work that way. And I think there's a real gentle comfort available to us if we can learn to sit peacefully with that. Consider, for a moment, how far human understanding has already traveled. Only a few hundred years ago, most people believed the Earth stood still at the center of a much smaller universe, with the sun, the moon, and the stars circling around it. Only about a century ago, most scientists believed the universe was static, unchanging, roughly the same size and shape forever, with our own Milky Way perhaps being the entirety of it. It was only in the 1920s that astronomers confirmed that the fuzzy little smudges of light they'd been observing in the sky, which they called spiral nebulae, were actually entire galaxies, unimaginably far away, each one containing hundreds of billions of their own stars. It was only in the 1960s that scientists found that faint, ancient microwave glow filling the whole sky, confirming that the universe had a hot, dense beginning. Human understanding of the cosmos has expanded almost as dramatically as the cosmos itself, again and again, generation after generation. Each new discovery revealing that the universe was larger, older, and stranger than anyone had previously imagined. There is no reason at all to think that this process has stopped, or that we've somehow reached the final complete picture of reality in our own particular lifetime. The question of what came before the Big Bang, or whether before even applies, may well be answered, at least in part, by scientists working right now, in universities and observatories around the world, quietly building the mathematics, refining the instruments, gathering the evidence that will eventually, someday, shift our humble, uncertain hypotheses into something closer to confident understanding. You get to hold that unfolding mystery gently tonight, not as a source of anxiety, but as a kind of quiet privilege. You are alive at a moment in human history when we know more about the universe than any humans who came before us. And yet we still stand, together, at the edge of genuinely enormous mysteries. There is something wonderfully humbling and wonderfully peaceful in that. You don't have to solve it. You don't have to hold the whole weight of not knowing on your own shoulders. Generations of careful, patient scientists are holding that weight together, slowly, steadily, the way a great cathedral gets built, not in a single lifetime, but stone by stone, across centuries, each builder trusting that those who come after will continue the work. Tonight, all you have to do is rest. Let your mind float gently at the edge of these questions, without needing to grasp them fully, without needing to pin them down. Let uncertainty feel for tonight less like an itch to be scratched, and more like a wide, dark, peaceful sky, full of stars you don't need to name in order to enjoy looking up at them. Breathe in slowly, and out. In, and out. Let's slow down even further now, and spend some time with a single word that keeps appearing in our story tonight. A word that seems simple, but is in fact one of the most slippery words in the entire English language. Nothing. When we ask, casually, did the universe come from nothing? We tend to picture something like an empty room, a blank page, a dark and silent void, stretching on forever, containing absolutely no objects at all. That's a very natural picture. It's the picture most of us grew up with, whether from religious teachings, from philosophy, or simply from everyday intuition about what empty means. But physicists, when they use the word nothing, are often describing something quite different. And it's worth resting here a while, letting the distinction settle gently over you, because I think it's one of the most important ideas in tonight's whole story. Picture, first, what philosophers sometimes call true nothingness or absolute nothing. This would be a state with no space, no time, no energy, no fields, no laws of physics, not even emptiness as a container, because a container, even an empty one, is already something. Absolute nothing wouldn't have a before or an after, because before and after require time, and time itself would not exist. It wouldn't have a where, because where requires space, and space itself would not exist. It's genuinely difficult, maybe even impossible, for the human mind to hold this idea steadily, because our minds evolved to think in terms of objects existing somewhere at some moment. Absolute nothingness resists that kind of picture entirely. Try, gently, to imagine it now, without straining. Notice how your mind keeps sneaking a faint, dark backdrop into the picture, a stage for the nothingness to sit on. That's all right. That's what minds do. True nothing may not even be something we're capable of truly picturing, only gesturing toward, the way you might gesture toward a color you've never actually seen. Now picture something different. The quantum vacuum we talked about earlier, which physicists sometimes casually call nothing, even though it's really a very specific, well-defined physical state. The lowest possible energy state of a quantum field, existing within the laws of quantum mechanics, still governed by rules, still capable of fluctuating, still, in a sense, humming quietly with potential. This kind of nothing already assumes quite a lot. It assumes quantum fields exist. It assumes quantum mechanics is already the operating rulebook. And in most versions of this idea, it assumes some notion of space and time, or at least the mathematical scaffolding that could eventually become space and time, already has some kind of existence. These are two very different kinds of nothing, and a great deal of confusion in casual conversations about the universe's origin comes from sliding back and forth between them without noticing. When a physicist says, the universe may have come from nothing, they very often mean the second kind, a quantum vacuum, or some deeper mathematical structure, not the first, philosophical kind of true, lawless, timeless absence. This matters gently for our bedtime story tonight, because it means the deepest version of the question, why is there a quantum vacuum at all? Why do the laws of quantum mechanics exist? Why is there any mathematical structure whatsoever, rather than utter, absolute nothing? Remains honestly outside the reach of physics as we currently understand it. Physics is extraordinarily good at describing how one physical state transforms into another, how a quantum vacuum might give rise to an expanding universe, how a contracting universe might bounce back outward. What physics has not yet managed to do, and perhaps cannot ever do, using its current tools, is explain why there is a coherent, mathematically structured something, even a humming, jittering, nearly empty something, instead of the deeper, absolute nothing that philosophers describe. Some physicists suggest this deeper question isn't really a physics question at all, but a philosophical or even a linguistic one, resting on assumptions about causation and explanation that may not cleanly apply once you've left the world of things existing in space and time. Other thinkers feel there must be some ultimate explanation, even if we don't yet have the concepts or the mathematics to express it. Both positions are held by careful, serious, intelligent people, and neither has managed to fully convince the other. I don't say any of this to unsettle you tonight, but rather to offer you a kind of permission. Permission to hold this deepest layer of mystery loosely, without needing to pin it down before you can rest. Even the most brilliant cosmologists, the ones who've spent entire careers pushing the boundary of what we understand back further and further, ultimately reach a point where they too must simply set the deepest why question down gently, unanswered, and go on living their lives, raising their children, teaching their students, watching sunsets, falling asleep at night, just as you're about to do. You get to do the same thing right now. Set the deepest why down gently, like a stone returns softly to still water, sending out slow, quiet ripples that spread outward, and gradually fade into stillness once more. You might be wondering, as you drift here in the dark, whether any of these ideas we've explored tonight, inflation, quantum tunneling, cosmic bounces, colliding brains, endless bubble universes, can actually be tested. Are these simply beautiful stories, elegant mathematics, with no way of ever checking whether they're true? Or is there some hope, however faint, of someday gathering real evidence? This is a wonderful question to rest with, because the honest answer is, yes, there is hope, and in some cases, scientists are already quietly listening for the echoes. Let's start with cosmic inflation, since it's the idea with the strongest current observational support among everything we've discussed tonight. If inflation really happened, tiny quantum fluctuations present during that unimaginably brief period of expansion would have been stretched out to enormous size, eventually becoming the seeds for all the structure we see in today's universe. The slight variations in density that grew over billions of years into galaxies, galaxy clusters, and the vast cosmic web of filaments and voids that spans the observable universe. These same tiny fluctuations should have left a very particular kind of fingerprint on the cosmic microwave background. That ancient light we talked about earlier, subtle patterns in its temperature and polarization that match remarkably well with what inflationary models predict. Space telescopes and ground-based observatories have spent decades now mapping the cosmic microwave background with extraordinary precision. And so far, the patterns they've found align beautifully with the predictions of inflation, which is part of why so many cosmologists take the idea seriously. Even though gently, it remains a well-supported hypothesis rather than a proven fact carved in stone. There's an even more exciting possibility on the horizon, one that scientists are actively working toward right now in laboratories and observatories around the world, while you rest quietly in your bed tonight. If inflation happened, it should have generated incredibly faint ripples in space-time itself, called primordial gravitational waves. The same general kind of ripple that the LIGO and Virgo observatories famously detected coming from colliding black holes. Though these primordial ripples would be vastly fainter, vastly older, echoes from that first fraction of a second after whatever we call the beginning. If scientists ever manage to detect these primordial gravitational waves and to measure their particular pattern, it could offer remarkably direct evidence about the details of inflation, and perhaps even hints about what came before it or what triggered it. What about the bouncing and cyclic models we explored? The idea of a previous contracting universe giving way, gently, to our own expanding one. Some physicists working on these models have suggested that a bounce, if it really happened, might have left its own subtle fingerprint on the cosmic microwave background too. A slightly different pattern than the one predicted by simple inflation, involving particular relationships between different kinds of ripples in that ancient light. Distinguishing between these competing fingerprints is difficult, and current observations aren't yet precise enough to fully settle the question. But future generations of telescopes, some of them already being designed and built right now, may be able to look closely enough to tell these stories apart. Even the more exotic, harder to test ideas, like the eternal inflation and bubble universe hypothesis, aren't entirely beyond hope. Some researchers have proposed that if our universe ever collided in its distant past with a neighboring bubble universe, that collision might have left an extremely faint, extremely subtle circular pattern in the cosmic microwave background, like the ripple pattern left behind when two pebbles are dropped into still water and their ripples cross each other. Scientists have actually searched the cosmic microwave background data for signs of such a pattern. So far, they haven't found any convincing evidence of one, but the search itself tells you something rather beautiful. Even our wildest, most speculative ideas about what came before the Big Bang are not simply idle daydreams. They make specific, checkable predictions, and dedicated, careful people are out there, right now, checking them. I find something deeply reassuring in that. The kind of reassurance that helps a mind settle down for sleep rather than spin with unanswered questions. These aren't just stories floating free of any grounding, the way an ungrounded dream might drift without direction. They are hypotheses, tied by careful mathematics to real measurable predictions, sitting patiently in the world, waiting for better instruments, more precise measurements, more patient decades of careful observation to finally confirm them, or to gently rule them out, making room for even better ideas. Let this thought rock you now, slow and steady. Somewhere, right now, in observatories in the Atacama Desert of Chile, in Antarctica, in orbit far above the atmosphere, sensitive instruments are quietly gathering ancient light, searching for the faintest of echoes from the very beginning, or from whatever, if anything, came before it. That listening continues, patiently. Whether you're awake to think about it or not, it will still be continuing tomorrow night, and the night after that, and for many nights to come, long after you've drifted off, long after you've woken again to a new day, long after this particular story has faded gently from your memory. Let yourself rest inside that patient, ongoing listening. You don't have to stay awake for it. The universe and the scientists studying it will keep listening quietly on your behalf. There's one more idea I want to walk through with you gently before we make our way, finally, towards sleep. An idea that connects several of the threads we've followed tonight, and that touches something a little more personal, a little more wondering, than pure equations and observations. If you look closely at the fundamental constants of our universe, numbers like the strength of gravity, the strength of the electromagnetic force that holds atoms together, the precise mass of a proton compared to an electron, the particular value of what's called the cosmological constant, which governs the accelerating expansion of space, you find something that has puzzled physicists for decades. Many of these numbers seem to sit within a remarkably narrow range that allows for a universe complex enough to form stable stars, complex chemistry, and eventually life. If gravity had been just a little stronger, stars might have burned through their fuel far too quickly for life to ever evolve on any surrounding planets. If it had been just a little weaker, matter might never have clumped together into stars and galaxies at all, leaving the universe cold, dark, and empty, thin gas drifting forever without ever igniting into starlight. If the strength binding atomic nuclei together had been even slightly different, the specific chemistry that allows carbon, and therefore life as we know it, to form inside stars might never have occurred. This apparent fine-tuning has led to a great deal of gentle, careful debate among physicists, philosophers, and cosmologists. Some see it as simply a brute fact about our particular universe, requiring no further explanation any more than the particular shape of a snowflake requires a grand explanation. Others feel the fine-tuning is significant enough that it calls out for some kind of deeper account. This is where the multiverse ideas we explored earlier gently return to our story, offering one possible account, though certainly not the only one. If there truly exist an enormous number of different universes, through eternal inflation's endless bubbles, or the many different possible shapes described by string theory's landscape, each potentially with different values for these fundamental constants, then it becomes far less surprising that at least one of them landed in the narrow range that allows for stars, chemistry, and life. This idea is sometimes called the anthropic principle. We shouldn't be surprised to find ourselves in a universe capable of supporting observers like us, because we could only ever have found ourselves in such a universe in the first place. A universe hostile to life would, by definition, have no one inside it wondering about its fine-tuning at all. There's a lovely, quiet way to picture this, if it helps you drift further towards sleep. Imagine an enormous field, stretching further than you can see in any direction, scattered with countless different seeds, each one slightly different from the others, each one capable, in principle, of growing into a different kind of plant, under different conditions of soil and sunlight and rain. Most of these seeds, scattered across most of that vast field, might never sprout at all, landing on rocky, barren ground, unsuited to their particular needs. But somewhere in that vast field, by simple probability, at least a few seeds land on exactly the right patch of soil, with exactly the right balance of water and light, and there, and only there, something grows. We are not surprised, walking through such a field, to occasionally find a lush, thriving patch of green, even surrounded by so much barren ground, because we understand that across such a vast field, with so many different seeds and conditions, at least some patches were bound to succeed. Our universe, in this picture, might be one such lush, thriving patch, not because it was singled out or specially designed, but because among a vast, perhaps endless scattering of different possible universes, at least some, including ours, were bound to land in a state capable of supporting the slow, patient blossoming of stars, of chemistry, of life, and eventually, of quiet minds lying in warm beds at night, wondering about the very field that grew them. I offer you this image gently, not as a settled answer, because it remains, like so much else in tonight's story, an open and actively debated hypothesis rather than a proven conclusion. Some physicists find it deeply compelling, others feel it explains too little, or relies on a multiverse we may never be able to directly confirm. But I think, even held loosely, even held with full honesty about its uncertainty, it offers something worth resting on tonight. The thought that however this universe came to be tuned so precisely, so delicately, in a way that eventually allowed for you, specifically you, to exist, to breathe, to wonder, to rest here. Now in the dark, listening to a quiet voice, talk about the edge of all things. However it happened, here you are. Improbable perhaps, precious, certainly. Woven, however it came about, out of the same deep physics that shaped galaxies and stars, and the ancient light still arriving from the beginning of time. Let that settle over you now, warm as a blanket. However unlikely the path, however uncertain the deepest explanation, the universe managed, after nearly 14 billion years, to arrange itself into a shape capable of you, resting here, breathing slowly, drifting gently towards sleep. Before we turn back to physics one last time tonight, I want to take a slower detour with you, out across human history. Because the question we've been exploring, what came before the beginning, is not a question that started with modern cosmologists in white coats, surrounded by equations and telescopes. It's a question as old as human beings themselves asked by every culture that has ever looked up into a dark, star-scattered sky, and felt that same mixture of awe and smallness that you might be feeling right now, wrapped in your blankets, listening quietly. Let's wander gently through a few of these old stories, not to compare them scientifically to the ideas we've explored tonight, but simply to notice how deeply, how universally human beings have always wondered about beginnings, and how often, across wildly different cultures, separated by oceans and centuries, similar images and themes quietly echo one another. In ancient Mesopotamia, in the region between the Tigris and Euphrates rivers, storytellers told of a time before the sky and earth were separated, when only a vast, undifferentiated water existed, personified as two great beings, Apsu and Tiamat, whose mingling waters contained, in potential, everything that would later come to exist. Out of that vast, watery beginning, the story goes, the gods themselves were eventually born, and the ordered universe, sky above and earth below, was slowly shaped and separated out. In ancient Egypt, several different creation stories described a similar, vast, dark, undifferentiated water, called Nun, stretching endlessly before creation, containing within it the potential for everything, patient and still, until the first mound of earth rose up from within it, and the sun god Ra first appeared, bringing light and order into what had been a formless, watery dark. In Hindu cosmology, as we touched on earlier tonight, time itself is imagined not as a single line with one fixed beginning, but as an endless cycle of creation, preservation, and dissolution, repeating across spans of time so vast they're measured in units called kalpas, each one lasting billions of years, with the god Brahma imagined as dreaming each universe into existence, only for it to eventually dissolve back into a formless potential, waiting patiently for the next great dream to begin. In several West African cosmologies, including traditions from the Yoruba and Fon peoples, creation stories describe a formless, watery void, out of which a divine being descends, bringing earth and order into what had been shapeless potential. Echoes, again, of water and formlessness slowly resolving into structure. In Norse mythology, the stories describe a vast, yawning emptiness called Ginnungagap, existing before the world was formed, flanked by a realm of fire on one side and a realm of ice on the other. And it was the meeting and mingling of fire and ice within that great emptiness that eventually gave rise to the first living beings, and eventually to the ordered world. And in the ancient Chinese tradition, one particularly beautiful story tells of a formless, egg-like chaos, dark and undifferentiated, out of which the being Pangu slowly grew, and upon waking, separated the heavens from the earth with a single mighty stroke, holding them apart as they gradually settled into their places, sky above, earth below, over the course of an unimaginably long stretch of time. I want you to notice something gentle and remarkable as these old stories drift past you tonight, one after another, like small boats passing slowly down a quiet river, again and again, across cultures that had no contact with one another, separated by vast oceans, vast mountain ranges, vast stretches of history. Human beings independently imagined the time before creation in remarkably similar terms. A formless, undifferentiated potential, often watery, often dark, often described as a kind of patient chaos, waiting to be separated, organized, and brought into order. Modern cosmology, in its own mathematical language, tells a story that rhymes with these ancient ones in curious, quiet ways, even though it arrived at its picture through entirely different means, through careful measurement, through equations, through the patient testing of hypotheses against evidence, rather than through myth and story passed down by firelight. And yet here we are again, still speaking, in our own modern words, of formless potential. A quantum vacuum humming with possibility, an inflating field of pure, undifferentiated energy, an endless boiling sea giving rise to bubble after bubble of order, a contracting universe collapsing back into a dense, unified potential before bouncing back outward into structure and form. I don't say this to suggest that ancient myths were secretly, literally describing modern physics, or that modern physics is simply myth dressed up in mathematics. That would flatten both traditions and do justice to neither. Rather, I think there's something worth resting on here, that the deep, patient wondering about beginnings, about the formless potential from which an ordered, structured universe somehow emerged, seems to be one of the oldest and most persistent threads in the entire history of human thought. Whether that wondering is expressed through the language of gods separating sky from earth, or through the language of quantum fields and inflatum particles, it comes from the very same place in us, a quiet, patient curiosity, looking up into the dark and gently asking, where did all of this come from? You are part of that very old, very human lineage of wondering tonight, lying here in the dark, letting these old stories and these new equations settle gently over you side by side, neither one cancelling the other out, both of them in their own way, honoring the same deep old question. Let your breathing slow further now, in rhythm with all those old, patient storytellers, all those old, patient astronomers, all of them, across every century, gazing up into the same dark sky, wondering the same gentle wonder that you're wondering right now. Let's take one more slow walk together before we return, gently, to the question of what may have come before everything. A walk not backward, past the Big Bang this time, but forward, through the enormous stretch of time that followed it, so that you can feel, in your bones, just how vast and patient the story of our universe really is. Picture, if it helps, the entire history of the universe compressed into a single calendar year, stretching from 1 January the 1st to the following December the 31st, a device some astronomers, including the wonderful science communicator Carl Sagan, have used to help human minds grasp timescales that are otherwise almost impossible to feel. On this cosmic calendar, the Big Bang happens in the first fraction of a second of January the 1st. The Milky Way galaxy, our galaxy, doesn't begin forming until around March. Our sun and our solar system don't form until early September. The first simple life on Earth appears around late September. It isn't until mid-December that more complex, multicellular life begins to appear. Dinosaurs don't arrive until around December the 24th, and they vanish in a great extinction on the evening of December the 30th. Human beings, in any form we would recognize, don't appear until the very last hour of December the 31st, and everything we would call recorded human history, every civilization, every war, every poem, every love letter, every scientific discovery, all of it, fits into the final few seconds before midnight. Rest with that image for a while. On this cosmic calendar, your entire life, however long or short, occupies a stretch of time far, far shorter than the blink of an eye. And the question we've been exploring tonight, what came before that very first fraction of a second on January the 1st, reaches back into a time so far removed from anything the human mind ordinarily experiences that it's genuinely difficult, even with a whole cosmic calendar to help us, to hold it steadily in view. And yet here you are, holding it. Gently, patiently, without needing to fully grasp its scale, the way you might hold something enormous simply by wrapping your arms partway around it and trusting the rest. There's something quietly humbling and also quietly comforting in walking through deep time this way. Humbling because it places your own life, your own concerns, your own worries about tomorrow into a context so vast that they shrink gently to their proper size, small and precious, rather than large and overwhelming. Comforting because it reminds you that you are the product of an extraordinarily patient process, one that took its time, unhurried, across billions of years, slowly building the conditions that would eventually allow for stars, for planets, for oceans, for the first fragile strands of life, for minds capable of wonder, for you, exactly as you are right now, resting in the dark. The universe did not rush to make you. It took nearly 14 billion years patiently, unhurried, gathering hydrogen into stars, forging heavier elements in their fiery cores, scattering those elements across space when those stars eventually died, gathering that scattered material once more into new stars, new planets, and eventually, on at least one small world orbiting one ordinary star, into the particular, remarkable arrangement of atoms that became you. You are allowed to take your time now too. There is no rush tonight. Just as the universe took its patient, unhurried billions of years to arrange itself into a shape capable of you, you can take all the unhurried time you need right now to simply drift, gently, softly, towards sleep. Let your thoughts stretch out now, slow and wide, the way the universe itself stretches out across that vast cosmic calendar. Each second of your falling asleep no more rushed, no more urgent, than the slow, patient blooming of a galaxy across 100 million years. There is nowhere you need to be. There is nothing you need to finish. There is only this slow, patient drifting, this quiet settling, this gentle rest. Let's return once more to the physics, gently, and walk through one more layer of the story. Not what came before the Big Bang exactly, but what happened in those first, almost impossibly early moments afterward. Because understanding this brief, strange age helps explain why physicists are so genuinely uncertain about what, if anything, came before it. If you could have watched the universe unfold from just outside it, which, as we discussed, isn't really a coherent idea, since there was no outside, but let's allow ourselves the image anyway, gently, as a kind of storytelling device, you would have seen something almost too strange for words. In the first tiny sliver of a second, temperatures were so extraordinarily high, and densities so extraordinarily great, that the four fundamental forces of nature that we experience today as quite distinct from one another, gravity, electromagnetism, and the two nuclear forces that hold atomic nuclei together, may have all been unified into a single force, indistinguishable from one another. The way white light contains every color of the rainbow, blended together into one. As the universe expanded and cooled, physicists believe these forces gradually separated out from one another, first gravity, and then, at a slightly later moment, the strong nuclear force, and then, later still, the electromagnetic force and the weak nuclear force splitting apart from what had briefly been a single, unified electroweak force. Each of these separations is thought to have released tremendous energy, shaping the young universe in ways still being studied today. For the first tiny fraction of a second, the universe was filled with a hot, dense soup of fundamental particles, quarks and gluons, moving freely, too energetic to bind together into anything larger. It wasn't until the universe cooled further, mere millionths of a second later, that quarks finally began binding together into protons and neutrons, the particles that would eventually form the nuclei of atoms. Then, over the next few minutes, physicists sometimes call this brief window the era of Big Bang nucleosynthesis. Protons and neutrons began fusing together, forming the very first atomic nuclei, mostly hydrogen, along with a good amount of helium, and just the faintest trace of lithium. This entire process, from a universe of loose protons and neutrons to a universe with its first simple atomic nuclei, took only about 3 minutes, and remarkably, the proportions of hydrogen and helium predicted by this theory match, with striking precision, what astronomers actually observe when they study the composition of the oldest, most pristine gas clouds in the universe today. But even after those first 3 minutes, the universe remained far too hot for electrons to settle into stable orbits around these nuclei, forming complete neutral atoms. Instead, for hundreds of thousands of years, the universe remained a hot, dense plasma, charged nuclei and free electrons, swirling together, constantly scattering light before it could travel very far, keeping the young universe essentially opaque, glowing but impenetrable, like the inside of a thick fog. It wasn't until the universe was about 380,000 years old that it finally cooled enough for electrons to combine with nuclei, forming the first stable neutral atoms in a moment. Cosmologists call recombination. Once this happened, light was finally set free to travel unimpeded across the universe. And it's this very light released at that moment that we detect today as the cosmic microwave background, stretched now after nearly 14 billion years of travel through an expanding universe, into the faint microwave glow we talked about earlier. I walk you through all of this tonight, not simply to recite a timeline, but because I want you to feel, in a gentle, bodily way, just how much happened, how much transformation, how much unfolding occurred in that first brief window of cosmic history. Forces separating, particles forming, nuclei fusing, light finally breaking free after hundreds of thousands of years of being trapped. And all of this detailed, carefully studied history happens after whatever we might call the beginning. The question of what came before reaches back even further than all of this, past the era of unified forces, past the quark soup, back to a time when the very concepts of particle and force and perhaps even space and time themselves may not have applied in any familiar way at all. This is why physicists speak so carefully, so humbly about the very beginning. We have an increasingly detailed, increasingly well-tested understanding of the universe's history, reaching back to a tiny fraction of a second after the Big Bang. But that final fraction of a second, and whatever, if anything, lies beyond it, remains genuinely at the frontier of human knowledge. A frontier that today's physicists are still mapping, patiently, one careful measurement at a time. Let this whole intricate unfolding rock you gently now, like a long, slow story told many times before, familiar and comforting in its retelling. Forces separating, particles cooling, nuclei forming, light breaking free at last after its long imprisonment in the fog. Traveling outward for billions of years, arriving finally, tonight, in the quiet instruments of patient scientists, and in the quiet, patient wondering of your own mind, right here, drifting gently towards sleep. Before we move into our final stretch of ideas tonight, let's rest for a while on something quieter, something a little less about equations and a little more about language itself, because I think it will help everything that follows settle more easily into your mind. Throughout tonight's story, we've used certain words again and again: before, beginning, cause, origin, as though their meanings were perfectly stable, perfectly obvious, no matter what context we place them in. And for most of our lives, in most situations, they are stable. When you ask what happened before breakfast, or what caused you to feel tired today, these words work exactly the way you expect them to. But words, like maps, are tools built for certain kinds of terrain. A map of city streets works wonderfully for navigating a city, and becomes useless the moment you try to use it to navigate the open ocean or the surface of the moon. In much the same way, words like before and cause are tools built by human minds, over countless generations, for navigating a world where time flows steadily forward, where events unfold one after another, where causes reliably precede their effects. At the very edge of the Big Bang, we may be asking these familiar words to navigate a terrain they were never built for. When physicists say that time itself may have begun at the Big Bang, they're suggesting that before, a word entirely built around the assumption that time already exists and flows forward, might simply run out of useful meaning at exactly the point where you'd most want to use it. It's a bit like reaching the edge of that city map and discovering, not that the city continues invisibly beyond it, but that the very concept of streets doesn't apply anymore, because you've stepped from a city into an ocean, where a completely different set of concepts, currents, depths, tides, becomes relevant instead. This is genuinely difficult to sit with, and I don't want to rush past that difficulty tonight, because I think honoring it, rather than smoothing it over, actually makes it easier to rest with. Our minds are built, through millions of years of evolution, to expect that every event has a cause, that every beginning has something before it, that time is an unquestionable backdrop against which everything else happens. These aren't just casual habits of thought, they're deeply, deeply wired into how human cognition works, useful for surviving in a world of predators and seasons and cause and effect. It makes sense that a question like, what caused the beginning of time, feels so natural to ask, and so unsatisfying to leave unanswered. But the universe, it turns out, is not obligated to make itself comfortable for the particular cognitive habits of a species of mammals that evolved on one small planet, orbiting one ordinary star, tens of thousands of years ago. The universe is allowed to be structured in ways that our intuitions, however deeply wired, simply didn't evolve to anticipate. This isn't a failure of the human mind, it's simply a reminder that our intuitions, magnificent as they are for everyday life, were never designed as a perfectly universal guide to the deepest structure of reality. Here is where I want to offer you something gentle to hold on to, instead of frustration, as you drift through this particular patch of mystery tonight. You don't need to resolve right now, in this moment, whether before the Big Bang is a meaningful question or a subtly confused one. Both brilliant physicists and brilliant philosophers continue to debate this very point, carefully, respectfully, without full agreement. What you can do instead is simply notice the strangeness. Let it wash over you like an unfamiliar but not unpleasant taste, and allow yourself to rest in the not quite knowing, the way you might rest in a hammock that sways gently from side to side, neither fully still nor going anywhere in particular, simply held, simply drifting. Language will keep failing us, gently, at the very edges of the biggest questions, and that's all right. Poets have always known this. Mystics have always known this. And now, physicists, working with the very best mathematics human beings have ever developed, are discovering it too, arriving at the very same soft, humbling edge from a completely different direction, only to find the same quiet, unanswerable hush waiting there for them. You get to rest in that hush now too, tonight, without needing a single word to carry you the rest of the way. Let's drift gently into one more idea before we begin making our way toward the end of tonight's story. A strange and quietly beautiful possibility that some physicists have taken seriously. What if time itself never actually began at all? What if, instead of a single starting point, time simply stretches infinitely backward, forever, with no first moment whatsoever? This might sound at first similar to the cyclic and bouncing models we already explored, but it's worth sitting with as its own, distinct idea, because it removes even the notion of a first cycle. In this picture, there was never a moment when time began, not even a first bounce, not even a first inflationary bubble. Time simply always was, stretching back through an infinite past, the way the number line stretches infinitely in both directions, with no smallest number and no largest number, just an endless, unbroken continuity. There's something both dizzying and deeply calming about this idea, and I think it's worth letting both feelings exist together, without rushing to resolve them. On one hand, an infinite past is difficult, maybe even impossible, for the human mind to fully picture. We're used to thinking in terms of beginnings and endings, first days and last days, the way our own lives have a clear starting point, and eventually, a clear ending point. An infinite past challenges that instinct at its very root. On the other hand, there's a certain deep peace in imagining that you are part of something that has simply always existed, in one form or another, an endless unfolding without an anxious, urgent beginning, without a single fragile moment when everything could have failed to happen at all. In an infinite past universe, existence isn't a surprising, precarious accident, balanced on the edge of a single beginning. It simply is, and always has been, patiently unfolding, the way a river doesn't need to remember its source in order to keep flowing gently onward. Some physicists have raised technical objections to models with a truly infinite past, related to certain mathematical theorems about the way expanding space tends to behave. But the question remains genuinely, actively debated within cosmology, without a settled answer. And I find that, tonight, rather than being frustrating, it's actually rather wonderful. It means the story isn't finished. It means there is still room, out there in the quiet dark of unanswered questions, for new ideas, new mathematics, new observations, perhaps even new ideas from scientists who are children right now, sleeping soundly in their own beds, dreaming about telescopes and equations they haven't learnt yet, who will grow up to spend their own careers turning these very questions over and over, the way we're turning them over gently tonight. Let that thought settle over you now, warm and slow. The story of the universe's beginning, or its beginninglessness, is still being written, and in some small, quiet way. Simply by resting your mind on these questions tonight, you're joining a conversation that stretches back through every human being who ever looked up at a star-filled sky and felt at once impossibly small and, somehow, deeply connected to something vast. We've spent nearly this whole story looking backward, toward the beginning, or toward whatever came before it. Let's take one more gentle detour now, in the opposite direction, and look forward, toward the far, distant future of the universe. Because I think it offers a kind of quiet symmetry that will help settle your mind before we finally close tonight's story. Just as physicists wonder what came before the Big Bang, they also wonder, with the same careful, patient uncertainty, what will happen to the universe in the almost unimaginably distant future. Not just millions of years from now, but trillions upon trillions of years, stretches of time so vast that even the cosmic calendar we walked through earlier can't quite capture them. Because on that calendar, the entire 14 billion year history of the universe so far was compressed into a single career. And the future we're about to describe would stretch on for countless calendars beyond it, one after another, essentially without end. Right now, astronomers know that the expansion of the universe isn't just continuing, it's actually accelerating, pushed along by something scientists call dark energy, a mysterious component of the universe whose true nature remains one of the great unsolved puzzles of modern cosmology, not unlike the puzzle of what came before the beginning. If this accelerating expansion continues indefinitely, the far future of our universe is thought to unfold something like this, slowly, gently, over spans of time too enormous to feel with ordinary intuition. Over the next 100 billion years or so, distant galaxies will continue drifting apart from us, faster and faster, until eventually, light from galaxies outside our own immediate cosmic neighborhood will no longer be able to reach us at all. The space between us, stretching faster than light itself can cross it. A future civilization, evolving on some world in the very far future, might look up into their night sky and see only their home galaxy and its close companions, with no other galaxies visible at all, no evidence remaining that a whole universe of galaxies ever existed beyond them. The way, if you only ever lived on a small cloud-covered island, you might have no way of knowing that vast continents existed beyond the horizon. Stars, too, will eventually stop forming, as galaxies slowly use up the gas and dust needed to birth new ones. The universe's peak era of star formation, it turns out, was actually billions of years ago, and we already live in a slowly dimming universe. Star formation gently declining, generation after generation of stars living out their lives, some ending gently, some ending in brilliant supernova explosions, without quite enough new material remaining to replace them all. Across trillions of years, one by one, the stars that remain will exhaust their nuclear fuel and go dark, some collapsing into dense white dwarfs, some into neutron stars, some into black holes, until eventually, in an era so far removed from now that numbers start to lose their ordinary meaning, the universe will contain no more actively burning stars at all, just their cold, quiet remnants, drifting through an ever-darkening, ever-emptier expanse of space. Even further into the future, some physicists suggest that protons themselves, the very particles that make up the nuclei of atoms, might eventually decay. Though this remains an open question in physics, tested but not yet confirmed. If protons truly are unstable over incomprehensibly long timescales, then eventually even the cold remnants of stars, even the simplest atoms themselves, might gradually break down into their most basic constituents, into light and the lightest of particles, drifting alone through an increasingly vast, increasingly empty, increasingly cold universe. Physicists sometimes call this extremely distant future scenario the heat death of the universe, a phrase that sounds dramatic, but which really just describes a state of maximum entropy, maximum disorder, where energy has spread out so evenly across such a vast expanse of space that nothing interesting can happen anymore. No stars, no chemistry, no structure of any kind, just a thin, cold, silent uniformity, stretching on perhaps forever. I want to be gentle with you about this image, because on the surface, it might sound like a sad place to end tonight's story, but I don't think it needs to be sad at all. And I'd like to offer you another way of holding it, one that might actually feel quite peaceful, especially at this hour, as your own body settles toward its own nightly rest. Notice, first, the timescales involved. We're not talking about anything that will happen soon, in any sense that could reasonably concern you or your children, or countless generations after them. We're talking about trillions upon trillions of years, a future so distant that our own sun, which will itself gently swell and fade in a mere 5 billion years or so, is barely a flicker at the very beginning of this long, slow story. There is no need to carry the weight of the universe's distant future on your shoulders tonight, any more than you'd lie awake, worrying about a rainstorm scheduled for 10,000 years from now, in a place you'll never visit, affecting people you'll never meet. And second, notice the shape of the story itself. A universe that begins, unfolds, blooms, with almost unimaginable richness and complexity. Galaxies and stars and planets, chemistry and life. Minds capable of wonder, capable of building telescopes and writing equations, and, yes, capable of quietly asking what came before the very beginning. And then, over spans of time so vast, they defy ordinary comprehension, gently settles back down again, into rest, into stillness, into quiet. There's a shape to that story that echoes something very familiar, something you experience yourself every single day in miniature. You wake in the morning, and the world blooms around you, full of activity, full of thought, full of motion. And then, as the day winds down, as evening settles in, things gradually quiet, gradually slow, until finally, gently, you settle into sleep, into stillness, into rest, your own busy mind quieting down the way the universe itself, across a vastly longer timescale, is expected to quiet down too. You are not separate from this story tonight. You are living out, on the scale of a single day, the same basic shape that the whole universe seems to trace out on the vastly larger scale of trillions of years. Activity rising, blooming, unfolding into richness and complexity, and then, eventually, gently, settling back down into quiet. Let yourself settle now, the same way. Let your own small, precious day come gently to its rest, the way the universe itself, so many trillions of years from now, will settle into its own long, quiet stillness. There's nothing frightening in this. It's simply the shape that things take. The shape that you yourself are taking, right now, drifting softly from activity into rest, from wandering into sleep. Before we close tonight, I want to tell you a little about the people behind these ideas, gently, unhurriedly, because I think it helps to remember that every equation we've walked through tonight was written down, slowly and carefully, by an actual human being, sitting at an actual desk, often late at night, often uncertain, often doubting themselves, just like you or I might doubt ourselves at the end of a long day. Albert Einstein, whose theory of general relativity underlies so much of what we've discussed tonight, spent nearly a decade slowly, painstakingly developing the mathematics needed to describe gravity as the curvature of space-time, filling notebook after notebook with false starts, crossed-out equations, and quiet frustration, before finally arriving in 1915 at the finished theory. He was, by his own admission, not a naturally quick mathematician. He worked slowly, carefully, returning again and again to ideas that didn't quite fit, patiently smoothing them out, the way you might slowly work a stiff, cold muscle back into ease. Georges Lemaitre, a Belgian physicist and Catholic priest, was among the very first to propose, in the late 1920s, that the universe was expanding from an extremely dense, hot early state, an idea he described quite beautifully as the expansion outward from what he called a primeval atom. At the time, many of his fellow scientists were deeply skeptical, including Einstein himself, who reportedly told Lemaitre that while his mathematics was correct, his physical understanding was abominable. Lemaitre, unshaken, continued developing his ideas patiently over the following years, and lived to see much of his once doubted theory gradually confirmed by observation. Stephen Hawking, whose work we touched on earlier tonight in discussing the no-boundary proposal, developed much of his most important research while living with a motor neuron disease that gradually took away his ability to move, and eventually to speak without the aid of a computerized voice. He continued working, continued publishing, continued lecturing to packed auditoriums around the world for over 50 years after his initial diagnosis, at a time when doctors expected he might have only a few years left to live, pursuing questions about the very beginning of time with a patience and a persistence that, honestly, I find quietly breathtaking every time I think about it. Vera Rubin, an astronomer whose careful, patient measurements of the rotation speeds of galaxies in the 1970s provided some of the strongest early evidence for the existence of dark matter, worked for decades in a field that at the time she began had very few women in it at all. She was once denied access to observe at a major observatory simply because there were no restroom facilities for women on site. The observatory eventually built one, so that her careful, patient work that would go on to reshape our understanding of what galaxies are actually made of, could continue. Andre Linde, one of the key architects of the eternal inflation theory we discussed tonight, has described the moment he first began to seriously consider the idea of an endlessly self-reproducing universe as one of quiet, almost dizzying wonder, sitting with the mathematics late into the night, slowly realizing that if his equations were correct, inflation might never fully stop, anywhere, creating universe after universe, without end, forever. I share these small glimpses with you, not to turn tonight's story into a history lesson, but because I think there's something deeply comforting in remembering that the biggest, strangest, most vertigo-inducing questions in all of science were pursued, patiently, gently, across entire careers, by ordinary human beings who also got tired, who also doubted themselves, who also, presumably, had nights much like this one, lying quietly in the dark, their minds still turning over unfinished equations, unresolved doubts, unanswered questions, before finally, eventually, drifting off to sleep themselves. They didn't solve everything. Nobody has. And yet, patiently, generation after generation, they each added their own small, careful piece to a picture that is still, even now, being filled in. You get to rest tonight inside the quiet ongoing work of all of them. The mathematicians and astronomers and physicists, past and present, who spent their careers gently pushing back the edges of the unknown, one patient calculation at a time, so that stories like the one we've shared together tonight could even be told at all. Let their patience become your patience now. Let their willingness to rest with unanswered questions become your own willingness too. You don't have to finish anything tonight. You only have to rest, the way they too eventually had to set down their pens, turn off their desk lamps, and sleep. Let's slow all the way down now, together, and spend a little while simply resting in your body, letting the physics settle quietly into the background, like a soft, distant hum, while we attend instead to something closer, something warmer, the simple, quiet fact of you, breathing, right here, right now. Feel the weight of your body against whatever is holding you up right now. A mattress, a pillow, a blanket pulled up close. Notice how gravity, that same gentle force we've talked about tonight, the force that shaped galaxies and pulled matter into stars, is also, right now, quietly holding you exactly where you are, pressing you softly downward, the same patient, invisible hand that has held every sleeping creature that has ever rested on this planet, held gently against the slow curve of the Earth, itself gently held in its long, patient orbit around the Sun. Notice your breath, in and out. Notice how each inhale draws in air made of atoms that have existed, in one form or another, since not long after the era we discussed earlier tonight, that brief window of nucleosynthesis, when protons and neutrons first fused into simple nuclei. The oxygen you're breathing right now was forged, much later, inside the heart of an ancient star, long before our Sun, or our Earth, or you existed in any form at all. That star lived and burned, and eventually died, scattering the oxygen it had made out across space, where it eventually became part of the cloud of gas and dust that condensed to form our solar system, our Earth, our atmosphere, and eventually After billions of years of patient chemistry and biology, the very breath moving in and out of your chest right now. You are quite literally breathing in the leftover breath of long-dead stars. There's nothing frightening in that thought tonight. I hope, instead, it feels a little like being held. You are woven, atom by atom, out of the same material as the stars we've spent tonight discussing, out of the same processes that shaped galaxies, out of the same deep, patient physics that may or may not trace all the way back to some ultimate beginning, or to no beginning at all. Let your shoulders soften now, a little more. Let your hands go loose and heavy. There is nothing for them to hold on to right now, nothing they need to grip or carry. Let your legs feel heavy too, sinking gently into the mattress beneath you, the way matter itself, across billions of years, gently sank into the gravitational wells that would eventually become galaxies, stars, and worlds. Feel your heartbeat, slow and steady, if you can sense it at all. A small, private rhythm, keeping its own quiet time, independent of the vast cosmic rhythms we've discussed tonight, and yet, in its own small way, part of the very same universe, obeying the very same physical laws, made of the very same fundamental particles that first came into being, or were always present, at whatever moment or non-moment marks the true edge of time. You don't need to hold on to any of the ideas from tonight's story anymore. You can let them go now gently, one at a time, the way you might release smooth stones back into a quiet lake, watching each one sink slowly out of sight, leaving only a few soft ripples behind, spreading outward and then, eventually, smoothing back into stillness. Let the balloon with its painted dots sink away now. Let the endless boiling sea of bubble universes sink away. Let the quantum vacuum, humming faintly with possibility, sink away. Let the bouncing universe, breathing in and out, sink away. Let the ancient stories of formless waters and separated skies sink away. Let the far, quiet future, trillions of years from now, sink away. Let all of it go gently, one soft ripple at a time, until only stillness remains. Only your breath, only your heartbeat, only the quiet dark around you, patient and unhurried, asking nothing of you now except rest. We're nearly at the end of our quiet museum now, so let's walk, one final time, softly, back through the rooms we've visited tonight, not to study them again, but simply to say a gentle goodbye to each one, the way you might walk once more through a house before turning off all its lights. In the first room, we stood at the edge of a map, where "Here be dragons" was written in careful, honest handwriting, marking the place where our equations stop working, where a singularity waits, not as a real physical point, but as a signal that our tools have reached their limit. In another room, we considered that time itself might curve gently at the beginning, the way the surface of a sphere curves, so that asking "before" might be a little like asking what lies south of the South Pole, not a hidden mystery, but a question quietly built on an assumption that stops applying exactly there. We walked through a room filled with a brief, violent stretching, inflation, expanding space by more than 1 trillion times in a sliver of a second, and beyond it, an endless boiling sea, producing bubble after bubble, universe after universe, without end. We lingered in a room, humming faintly with quantum jitter, where something might arise from a strange technical kind of nothing, though the deepest, most absolute nothing remains forever just out of physics's reach. We walked through rooms holding a cosmic breath, in and out, contraction and bounce, cycle after cycle, perhaps forever, and a grainy structure to space itself, fine enough to catch a falling universe before it ever reaches a true infinite point. We wandered a garden of countless other universes, blooming according to countless different rules, and we sat for a while with the comfort of simply not knowing, letting that comfort settle like a warm blanket instead of an uncomfortable itch. We visited old rooms too, filled with ancient stories of formless waters and separated skies, told by firelight long before telescopes existed, echoing gently across centuries and oceans, the very same wonder we carry with us tonight. And we walked forward too, into the far, quiet future, trillions of years from now, watching the universe's own long day wind down into its own eventual rest, tracing the very same shape that your own day is tracing right now as you settle towards sleep. Every room in this quiet museum stays exactly where it is, waiting patiently for you whenever you'd like to visit again, tomorrow night or any night after that. Nothing you've heard tonight needs to be carried forward into tomorrow. You can leave all of it here gently in these quiet rooms and simply walk out now into the dark hallway and from there into sleep. I want to offer you one more image before we begin drifting towards sleep together. One that I find particularly soothing, and I hope you will too. All of these ideas we've explored tonight, inflation and eternal bubbles, quantum fluctuations in a jittering vacuum, cyclic universes breathing in and out, colliding brains drifting through higher dimensions, an infinite past stretching backward forever, a no-boundary universe with no edge to fall off of. All of these ideas, as vast and strange as they are, live inside something small and warm and entirely human. The quiet, patient curiosity of people who simply wanted to understand. Physicists studying the origin of the universe are not so different in a way from a child lying in the grass on a summer evening, looking up at the first stars appearing in a darkening sky, and asking quietly, where did all of this come from? The mathematics has grown enormously sophisticated, the instruments enormously precise, but underneath all of it is the very same simple wonder, the very same soft, patient curiosity you might have felt yourself as a child, or might be feeling right now, tonight, as you drift towards sleep. You don't need a degree in physics to feel connected to this story. You don't need to understand the equations behind loop quantum cosmology or the string landscape to feel the same quiet awe that drove the physicists who developed them. The wonder comes first. The mathematics comes later, built carefully on top of that first simple feeling of looking up and asking why. So tonight, let yourself feel that wonder, gently, without needing to chase it any further than feels comfortable. You have traveled, in your mind, across the entire history of the universe and beyond it, into realms that may forever remain hypothetical, may forever remain just beyond the reach of direct observation. And that's all right. The traveling itself, the wondering itself, is enough. Somewhere above you right now, though you may not be able to see it, if you're indoors, if there are clouds, if there's too much light around you, the same vast sky is turning slowly overhead. The same ancient starlight is arriving. The same faint cosmic microwave glow is washing gently across everything. A whisper from a time before there were any eyes at all to notice it. You get to rest inside all of that tonight. Small, warm, safe, held gently within a universe so vast that its beginning, or its beginninglessness, remains one of the greatest open questions human beings have ever asked. Let your body grow heavier now. Let your thoughts grow softer, slower, quieter. If you like, picture yourself once more as that child lying in the summer grass, looking up at the first stars appearing in a darkening sky. Feel the cool ground beneath you, the last warmth of the day still rising gently from the earth. Notice how the sky doesn't ask you to understand it in order to enjoy it. It simply spreads out above you, wide and dark and scattered with light, patient, unhurried, exactly as it has for longer than anyone can easily imagine, and exactly as it will continue to be long after tonight, long after you wake tomorrow, long after every question we've explored together has either been answered or has quietly dissolved into a better, gentler question we haven't yet learned to ask. You don't need the answer to rest peacefully beneath that sky. You never did. The wondering itself, held loosely, held gently, without urgency, without struggle, is enough. It always has been. We're nearing the end of tonight's journey now. So let's slow all the way down, together, the way a long, winding river finally widens and slows as it nears the quiet sea. We began by wondering what existed before the Big Bang. We walked gently through what scientists actually know for certain: an expanding universe, ancient light still arriving from the distant past, powerful evidence of a hot, dense beginning roughly 13.8 billion years ago. We stood at the edge of the map, where our equations dissolve into mathematical infinity. A blank space marked, honestly, we don't yet know. We considered that time itself might not extend past that edge at all, the way there's no south of the South Pole. We drifted through an unimaginably brief moment of cosmic inflation and an endless boiling sea of bubble universes stretching on forever. We considered a universe born from the strange jitter of the quantum vacuum. We pictured a cosmic breath, expanding and contracting, over and over, forever, and a quiet, grainy structure to space itself that might prevent the universe from ever truly reaching a singular point, bouncing gently outward instead. We wandered through a garden of possible other universes, each one blooming according to its own laws. We sat with the comfort of not knowing, and let that comfort settle over us like a warm blanket. And we considered, finally, that time itself might never have had a beginning at all, stretching backward infinitely, patient and endless. None of these ideas on their own are certainly provably true, and that's all right. That's more than all right. That's simply where the edge of human knowledge currently stands, and it's a beautiful, humbling place to stand together tonight. You don't need to remember any of the details now. Let them all blur softly together, the way a painting blurs when you take off your glasses, colors bleeding gently into one another, shapes softening, edges dissolving, balloons and bubbles, bounces and brains, an ancient light still traveling, a quiet, patient not knowing, resting easily in your chest instead of pressing anxiously against it. Feel your body now, heavy and warm against the mattress beneath you. Feel your breathing, slow and even, rising and falling like some small, quiet universe of its own, expanding gently with each inhale and softly contracting with each exhale. In and out, in and out. There is nothing you need to do right now except rest. Nothing you need to figure out, nothing you need to solve. The universe took nearly 14 billion years just to arrange itself into a shape where you could exist at all, lying here, warm and safe, wondering gently about beginnings and endings. It can certainly wait a little longer for you to drift off to sleep. Let your eyelids grow heavier. Let your thoughts grow softer, farther apart. The way stars grow farther apart as the universe expands. The space between each thought stretching gently, slowly, comfortably, until the thoughts themselves grow quiet and distant and eventually fade. You don't have to know what existed before the Big Bang tonight. You only have to rest. Somewhere above you, the same ancient light is still traveling, patient, unhurried, arriving after billions of years of silent journey through the dark. Let yourself be just as patient, just as unhurried. Let's count that patience out gently now, together, the way you might count slow, easy breaths, with nowhere else to be. 1. A quiet room, dim and warm, holding you exactly as you are. 2. A slow breath in, filling your chest gently, without effort. 3. A slower breath out, releasing anything you've been holding on to today. 4. Your eyelids, heavier now, resting fully closed. 5. Your jaw, soft and loose, no need to hold it tight. 6. Your shoulders, sinking a little further into the mattress beneath you. 7. Your hands, open and still, asking nothing of the world right now. 8. Your legs, warm and heavy, at rest. 9. Your whole body, settling, the way dust settles slowly through still water, drifting down, down, gently down, into quiet. 10. And just breathing now. Nothing to solve, nothing to hold, nothing to figure out before you're allowed to sleep. If your mind wanders back, even now, to balloons stretching, or bubbles boiling in an endless sea, or a universe breathing slowly in and out across countless cycles, that's all right. Let the images drift lazily past, the way clouds drift across a summer sky, never demanding your full attention, never needing you to follow them anywhere in particular. Just clouds passing quietly overhead, while you rest safely on the ground below, warm, still, unhurried. The universe took nearly 14 billion years to arrange itself into a shape capable of you. It is in no rush tonight, and neither are you. Whatever existed before the Big Bang, an eternal inflating sea, a quantum fluctuation, a bounce from a previous contracting universe, a boundaryless beginning with no before at all, or something else entirely. Something no one has even imagined yet. It can wait, patiently, for science to slowly, carefully, gently uncover it. One careful measurement at a time, across however many more decades or centuries that takes. And you, right now, get to simply rest, held by gravity, held by warmth, held by the quiet dark, held by the same patient universe that made the stars, that made the earth, that made you exactly as you are. Let your breathing continue on its own now, slow and steady, needing no attention from you at all. Let your thoughts grow quieter, softer, farther apart, like stars drifting slowly apart as the universe expands, the space between each one stretching gently, comfortably, until eventually they fade from view entirely, and only stillness remains. You don't have to know what existed before the Big Bang tonight. You only have to rest. Slowly. Gently. Safely. Drifting now, softly, into sleep, the way the whole universe once drifted, and perhaps will always drift, from mystery, into being, into quiet. Good night.